heat exposure, our body reacts in a manner such as excess sweating, we may feel metabolism gets affected, and at the same time there are various cardiovascular impacts that you may experience on our body. Now, why this topic is of interest to us, as just shared by my colleagues in the presentation before, we don't have the exact data. However, the data prepared by Gallagher says that approximately 71% of the workers around the world, they are exposed to heat. And with climate change, as the temperature of the planet increases, and by 2030, we are expecting that the temperature of the planet will increase from anywhere between 1 to 5 degrees Celsius. So we are expecting the impact will be more severely felt by those who are working under the sun. It includes outdoor labor, it includes sports people, athletes, and anybody else who is outside for a longer time. So the longer time you are exposed to heat, the more you are going to experience these physiological changes. So what we are looking at, what we are looking at is heat acclimation. How does our body react to exposure to heat? Now you may find it familiar to another term, which is heat acclimatization. Heat acclimatization is a natural process with the help of which our body gets adapted to the increasing temperatures. However, heat acclimation is due to repeated exposure to heat, and because of which our body reacts in a manner such as our body's temperatures rise, we start sweating a lot, and we experience cardiovascular, you can say, physiological changes as well. Of course, our colleague just explained to us how it leads to mortality as well, okay? So here, what we are going to look at is we are going to understand the biomarkers. Biomarkers are those proteins, those genes, those characteristics which will help us to predict what might be the outcome, or which proteins are linked to which kind of physiological conditions that we are experiencing. So what we did in our study is, we have a lot of research being conducted in the past in this area. Like a lot of research studies are conducted in understanding heat stress related aspects. There is research on heat shock proteins. There is research on plants. There is research on animals. However, we still need a lot of research on how humans react, or how humans get used to it. And moreover, for that, we need to understand the physiological, we need to link the physiological changes with the proteins. So what we did is, we looked at the data which was made available by the researchers who conducted a research in Canada. And the researchers, Gagnon et al., they have shared their data on these websites. So from there, we took the data and we conducted 4 different, 4 tiers of analysis. The data which they had, which we used, was based upon the experiment that they conducted on 10 different individuals. As we see, the details of the data sets are provided to us here. I will not spend a lot of time here, but the data is available, as I said, here on this website. On this link, you can access the data. And the researchers said that they have, of course, kept it open for us to experiment further. So these were the key findings that the researchers arrived at. But however, again, they did not tell us exactly which proteins are leading to which particular physiological change. And that's where we came into picture. We conducted a multi-tier analysis, and our analysis is into 4 tiers. We conducted a descriptive analysis first. Total more than 9,600 proteins were identified, the original researchers. We narrowed them down, and we identified, through the multi-tier level analysis, we identified the exact proteins that can help us to predict the physiological conditions. So we conducted a descriptive analysis, then a predictive, and we are further in future, we are planning to do something better, which will help us to substantiate it. So these are the 4-tier levels or 4-tier pathway that we followed for the analysis purpose. Tier 1 is essentially aimed at finding out which proteins change. As I said, more than 9,600 proteins were identified and the data sets were provided by the previous researchers. So we need to narrow it down further to understand which proteins are predicting the changes. Moving on, tier 2, we did correlation analysis to identify the relationship between specific proteins and the physiological outcomes. Then we prepared a predictive modeling using specific techniques, and then the last one is we prepared an integration and a pathway was provided to us. Each of these levels of analysis we conducted has specific purpose. As I just mentioned, tier 1, the purpose was to identify how plasma protein concentrations change in response to the heat exposure. Remember, we didn't collect the data was collected by the researchers, and they collected the data by exposing the participants to heat at a specific interval. So that's what they did, and we just analyzed the data the way we tried to, suitable for our research purpose. Then second tier analysis, we conducted correlation analysis. The purpose was to examine the proteins which are related to specific body changes, such as heart rate, sweating, and blood flow. The tier 3 analysis helped us to identify those proteins which are predicting the physiological outcomes. And the fourth tier, which we used basically to select the proteins which appear the most when we conducted the analysis. So the outcome of this is, I will just try to show you with the help of the dashboard that my colleague has prepared. Sorry? Locked? So this is how the dashboard looks like. We just entered the data and scroll. This is the overview of how many proteins and the analysis summary. This is where we were able to identify at each level. Go to tier 1. At each level, we conducted the analysis, and as we see the findings that once we completed the tier 1 analysis, we were able to narrow down from approximately 10,000 proteins to 825 proteins were identified to be significant. And these are the plots which can help us to identify. These are the proteins, the abbreviations that we find. These are the different types of proteins which were shortlisted in this level of analysis. Tier 2 analysis, we applied Spearman's correlation analysis. By the way, analysis is done using Python. So Spearman correlation analysis was applied, and from here we found out the relationship between significant protein and physiological correlations. We were able to narrow it down further, and we found out there were 1,439 unique proteins which were showing relationship with the different physiological conditions. And this is the analysis, this is the visualization of that part. Tier 3, we conducted elastic net regression analysis, which helped us to handle the issues with autocorrelation, because we have so many proteins and maybe many proteins are predicting the same physiological condition. Hence, we applied elastic net regression, which helped us to narrow down, and we were able to identify specific proteins which were linked to specific physiological condition. So this is the, sorry, this is the visualization of the data analysis that we did. Lastly, in tier 4, we integrated all the 3 tiers and we identified that there were 377 proteins which were validated or which were also common across all the 3 tiers. And this is how our dashboard gives us an idea, a better visualization of the analysis that we did. The biological pathway for which we used enrichment analysis, which was basically to help us to analyze proteins and identify the biomarkers which are responsible for the specific physiological condition. And as you see, if we come back to the PowerPoint presentation, then this is how the same results are summarized for us. The final shortlisted, we have 7 biomarkers, which each of them, like for example, there is TIMP. This particular protein predicts the cardiovascular physiological outcome. IL presents the, or it is linked to sweating. Similarly, PRL is linked to metabolism. Now the question is, why did we do all of it? What is the implication of it? Of course, as I mentioned, considering more than 71% of the total workforce in the world is working outdoor, and with increasing heat exposure, we will be experiencing the physiological conditions getting affected by them. If we understand which protein can predict what kind of physiological outcome, definitely medical health-related intervention can be taken. Specifically, heat acclimation is an important component, specifically in this part of the world, because we are, as just my colleagues mentioned, there are many workers who work outdoors. There are not just construction workers, others as well. And when they are regularly exposed to heat, we are going to experience health-related, I would say, increasing health-related issue. I wouldn't say health-related crisis, but definitely increasing health-related challenges we will face around the world. So that's the reason why it is important that we understand the implications of it from industry perspective as well as from health-related and from medication-related perspective as well. So these are the key findings, and these are the tests that we applied, and as we showed it in the dashboard, these were the findings that we identified. So what do we want to do with this finding? How are we going to work on this finding, or how we are going to extend it further? As I said, this data is from Canada. So definitely we will say, or we can say that maybe something which is applicable in that part of the world cannot be exactly replicated in this part of the world. However, understanding these proteins tells us how we can address these physiological conditions in a more focused manner. Plus, in order to fill the gap wherein we don't have any data from this part of the world, we are planning to conduct this experiment on outdoor workers within UAE. And for that, we are going to use wearable devices, and we are going to collect data of their physiological changes over a period of time. So this is what we intend to do. This is the intended heat stress early warning system that we are trying to work on, which can help us address this particular challenge that people, outdoor workers, as well as athletes, military personnel, and all the outdoor workers may face. So thank you very much for listening to me very patiently.
Any questions? Questions? No?
I was so clear.
Right.
Thank you very much.
Any question? I have a question.
Yeah, please.
Yeah. So you did a statistical test for all those biomarkers, just to see that there is a significant correlation between the biomarker and then the response to heat?
Yes.
For all of them, eh?
Yes. And at each stage, the number of proteins which were acting as predictors or which were showing correlation were reduced. You know, the data was treated multiple times to arrive at only those proteins, because some of the things which we'll find over here related to biomarkers is what matters is the NPX value, that is normalized protein expression values, which are important for us to identify proteins which are predicting the physiological condition. So only those NPX values which were high, which were supposed to be significantly predicting physiological changes, were retained. And that's how the number of proteins reduced at each stage of analysis.
Okay, so living in England, you know, where it's cold, I have to confess I like to go to sauna 2-3 times a week. You know, after your talk, you know, I think you convinced me to go more often, to be better adapted to climate change, right?
Definitely, definitely. Okay,
Good.
thank
Any
you
other
very much.
question? No? Then we'll go to the next.
Thank you.
And last but not the least presentation, which is called Intervention Analysis in Causal Bayesian Networks to Mitigate Mental Health Risks from Natural Disasters Application to Flooding. Yeah? Presented by Syed Musavi and Alireza Daneshka.
Yes, perfect. Do you have what time is it? Yeah, well, what time is it? I don't have watch. Yes, and what time is it now? 3:30. Okay. Hello, and thank you for attending my seminar. Okay, so what I'm going to present first, introduction, then data that we use, then methodology, some results, health economics, because we deal with economics side as well, and finally conclusion. So let us start with introduction. Background. You know, natural disasters such as floods are very well known for their catastrophic physical damage, as we see in news. And there was one, unfortunately, a recent one you might have heard just yesterday. I heard that in the news. So we know them because we see lots of physical damage, damage to building, etc. But that's not the only damage. And in fact, their catastrophic mental health damage could be much worse. But we often underestimate that because we don't see that as we see physical damage. So we don't see what is inside the mind of people. That's not well visible as are damages to building. That's why mental health aspect of natural disasters are often underestimated. And good thing is that in recent years, people have recognized this gap, and gradually there appear research work about mental health aspect of such natural disasters. So so more and more research papers published in this area. That's good. For example, Clore et al. 2025 study which factors are most influential on mental health conditions after natural disasters. Another work goes further and proposes some strategies to reduce mental health aspects of natural disasters. Another one by Sadiqi et al. And my colleague Professor Ali here proposed a novel approach based on Bayesian networks to not only model which factors affect mental health conditions, but also how to analyze their economic aspect. But that's just a starting point, really, just the initial idea. So although there are some work in the literature, but there is still a lot to do. How about this research? This research continues with the idea by Sadiqi et al. On using Bayesian network. So we propose a special type of Bayesian network called causal Bayesian network in order to model which variables affect mental health conditions and also model the relationship between those variables. In particular, we cover 3 types of mental health conditions, namely depression, anxiety, and post-traumatic stress disorder, or PTSD. What we want to do after we create the model, we want to analyze intervention. What do you mean by intervention? For example, suppose that one of the variables that affect mental health is, let us say, loss of home, financial aspect of the disaster. So what if government supports people who are affected? So would that make a big change or not? How about other variables? For example, having an early warning system in place. Would that be very helpful or not? So we call these interventions, and we want to analyze what happens if we apply such interventions. An important part of the research is to analyze the economic aspects. So for each intervention, there is cost. Of course, if government wants to pay for the financial loss of everyone, of course, that's costly. So we need to know the cost. But we need to also calculate the cost of saving, preventing those mental conditions. So to see which one outweighs the other. So economic aspect is also important. That's part of the research. And this research is ongoing. It's not finished. It's ongoing. And this is just a short report of what's happened so far. So these are the objectives of this research. Okay, let's just move on to the second part, which is data. For this project, we do not have real data yet, although we have been talking with UK HSA to give us some data, and it is promising. We have got the variables from them, but not yet the actual data. So what we have done, we have created some synthetic data based on those variables, but we hope that we will receive the real data soon. So that's a UK Health Security Agency, or UK HSA. And they have given us the variables. So here, in fact, the data is just questionnaire. They interviewed people after a flood happened about 13 years ago. They interviewed around 1,000 people, and the interview has about 200 questions. So we know the questions and we know possible answers, and based on that, we created some synthetic data. So we generated 1,000 rows of data, simulating 1,000 respondents. And the question has different parts, for example, demography, such as age, sex, education, employment, flood exposure, water depth, structural damage, etc., etc. We generated demographic data randomly. Well, the rest were also generated randomly. However, we tried to somehow mimic real data by some methods. In particular, what we did, we assumed that 20% of people have been affected severely by the flood, and 40% medium level, 30 low, and 10% minimal. So we considered 4 categories of people, depending on the extent they were affected by flood, and based on those groups, we generated the rest of the data randomly. For example, for those who were affected with high severity, the first blue row, we considered physical symptoms distribution as 40 non-40 mild, 20 severe. But for those with minimal impact, So the majority, 85%, none, no physical symptom, and just 2% with severe physical symptoms. So we generated things randomly, but we try to shift it to our real data somehow. Similarly, for other questions, for mental health items, we did a similar approach. And we followed this pattern for 96% of cases, and we allowed 4% to use just uniform probability distribution to make it more random. So what we have done in generating synthetic data is not perfect at all, and is just to have some data in order to implement the method. So so far our contribution has been just the methodology, really, not generating data. But we hope that we will soon receive real data. So what about methodology? As said, we use Gaussian Bayesian network in order to model the impact of various variables on those three mental health conditions: depression, anxiety, and PTSD. But not only that, but also to model the causality among the variables as well. So which variable affects which variable? Then we conduct intervention analysis. And about the structure of the network, we use the literature, and we use our, ideally we should do expert elicitation, so we treated our team as expert. It's not ideal, but better than nothing. But we are in contact with experts in order to revise the structure. And you know, for Bayesian network, one thing is the structure itself, but the second thing is something called conditional probability tables, which means, for example, suppose that two factors affect one. So what happens is if factor 1 is low, factor 2 is low, so what is the probability for the outcome to be low as well? So probability of the outcome depending on probability of the causes. So this is the network we have so far designed. As you see, there are lots of boxes. Those are variables, and the links suggest that which variable has some effect on another variable. For example, here this variable affects this variable affects this variable. Those red ones are the three mental health conditions, and those yellow ones are where we suggest intervention. For example, one of them is financial loss. So this is one potential suggestion for intervention. For example, government try to compensate financially. So what happens if we do that? Okay, the relationship between this network and the questionnaires is that we designed this network based on the data that we have that come from the questionnaire, but there is no one-to-one correspondence. It's not the case that one of the questions is this one this one that one. For some of them, that's the case. For example, for homeowner, there is one single question that asks, are you homeowner, yes or no? But for some other nodes, for example, water damage, there are more than one question. Therefore, we combine the result for those answers into one single value for this node. And for some other nodes, such as financial loss, there is no direct question, actually. It is affected by several variables, and those variables are calculated based on the questionnaire that we have. So variety of a combination. Okay, so short result. What we did, we applied intervention on three variables: financial loss, emotional loss, and physical health loss. And tried to observe what happened to those three mental health conditions if we somehow prevent financial loss or emotional loss or physical health loss. For financial loss, these are the results. We have three bar charts, as you can see, one per mental health condition. This is for depression, this is for anxiety, this is for PTSD. But let us focus on one of them. For example, depression. You see blue, you see light blue and dark blue. Light blue shows the priority distribution before intervention, and dark blue I'm sorry, the dark blue before intervention and the light blue after intervention. So why are there three of each color? For depression, we have considered three levels. No depression to low, the first one, medium and high. So ideally, in perfect world, probability of low should be 1 and the other two should be 0, but that's not the case. So before intervention, the dark blue shows the probability distribution. The sum is 1. And after intervention, what happened? You see that light blue is larger here, the increase. The probability of depression to be nothing to low is now higher, and instead the other two are lower. This is what we expect. Yeah? So if we somehow prevent financial loss, then we expect increase in 0 to low amount of depression, and the other two are decreased. So similar pattern can be seen for the other two diseases. So this is for one single intervention, which is on financial loss. How about the other interventions? Emotional loss, similar pattern, not exactly the same though, and physical health loss. You see here, probability of depression to be nothing to low is increased here using using light blue after intervention, but not here. So this one is odd. But apart from that, all the results made sense. This table summarizes, let me go back here and explain something. You know, here we have 3 bars. What if I want a single value? What we can do, we can calculate the expected value. So for each color, before intervention or after, we can have one single value, which is the expected value of depression. In that case, we can just compare those values before and after intervention. For example, for intervention on financial loss and to consider its impact on depression, we have 2 values which are expected values. So before intervention, expected value is 1.03, and after 0.8, so we have 16% reduction approximately. So this gives a metric to see how well we did and how effective is the intervention. So we have 1 row per intervention and 1 column per 1 category for each disease. Yeah, these are the results. However, please note that we use synthetic data, so we can never rely on these values really. We just wanted to showcase the methodology. For example, you see, while these values all make the sense, this one does not make sense. This is negative. But remember that we are not using real data. But overall, I mean, 8 out of 9 cases we see the values make sense. So we applied another intervention on insurance grant. We expected reduction in mental health condition, but we didn't see that really. But again, that could be because the data is not real. Okay, so we just presented the methodology. How about the economic aspect? Okay, so because we are not using real data, we cannot do perfect economic analysis, but we can showcase the methodology again. Let us assume that the probability of depression is 0.65 before intervention and 0.55 after some intervention. Right? So we get a 0.10 reduction in probability of depression. So how can we convert this to money? From one hand, we get benefits. So what are the benefits? Healthcare costs. So if someone has depression, it imposes cost. So in the UK, it imposes cost on NHS. Here, people pay. So it doesn't matter whether people pay or NHS pays, so eventually it has some cost. So we save that cost if we completely eliminate depression. Is this the only cost that we can save? No. Productivity loss cost. So if I have depression, then I'm not as productive as a healthy one, right? So if you manage to restore my full health, I don't have depression, then my productivity is maximum, and then this is also money. So it contributes to the benefits. And another one is quality of life. This quality of life is a metric used in this context. Let me explain it this way. A completely healthy person living for 1 year gets 1 mark. So number one means someone lives for 1 year without any problem. And if someone is dead, then that's 0. Well, we can assume that everyone has value greater than 0, but no more than 1, based on their health level. So we can take into account that value. It comes with another metric called willingness to pay. That's also in the context of health economics. That means the amount of money that someone is ready to pay in order to live healthy for 1 year. So this is to convert life to money. There is some ethical criticism about this. People say, well, you cannot monetize life. Life is so valuable. We cannot compete with money. So there are lots of discussion about this. So hopefully in this research, we will not use a given value for this willingness to pay. Hopefully we can compare interventions parametrically. We say intervention 1, for example, saves 2 WTP. Intervention 2 saves 3 WTP. Therefore, the other intervention is better. We try to avoid monetizing it, to avoid those criticisms. But these are the methods that are usually used. Okay, so this is an example. Suppose that the difference in the probability of depression is delta P. It's 0.10 in that example. N is the number of people in the population. Uptake is the proportion of the population that you can reach. When you want to do intervention, in ideal case, your intervention covers everyone, but in practice that's not the case. For example, 80% of people may benefit from that. You may reach 80% of people. So we need to calculate uptake. Persistence is about how things change over year, because depression can last for years, and therefore its benefit can last for years, and intervention similarly. So both intervention and those mental diseases can last over years. They are not just matter of single year. But let us keep things simple. Let us assume that we are talking about 1 year. In that case, t is 0. So year start with 0. So if we consider t is 0, this one goes, and just eliminate t for now for simplicity. In that case, n averted means the expected number of people who are affected, which is the total number of population by the difference in the probability of depression product uptake. Now, what are the benefits? There are 3 benefits in this model. We save cost of healthcare, cost of productivity, and cost of quality. And this is multiplied by the number of people who are affected. That's not for one single person. Those are benefits. And then we need to calculate cost as well. However, calculation of cost of intervention really depends from one intervention to another. And we couldn't just formulate it. It heavily depends on the intervention itself. If we want to consider impact over several years, more than 1 year, we can consider discount factor. I mean, over years, both the benefit and the cost are discounted at some rate. For example, this is one possible formula for that, but let us ignore that to make things simple. If we ignore that, so let us forget about this discount factor. Then one metric to see if the intervention is useful or not is just simply calculate benefit minus cost. This is very simple, benefit minus cost. This is over years, but if you consider 1 year, we only have this one. We can consider the difference. This is called net present value. Another possibility is to divide benefit by cost. We expect this to be more than 1, and we expect this to be more than 0. So what we do this for several interventions and see which one is more cost effective, and choose that one. Here is an example of calculation. For example, for that case when we had a 0.10 difference in probability of depression, assume that 80% of people will be covered, will be reached by the intervention. Then, assuming that we have 1,000 people in the population, then we calculate the product, and the expected value of people who are affected is 80. That's it, that as if we have 80% change from full depression to no depression completely. Then I don't know if you have time. You have time to go through. Okay, no, then I stop here. Thank you. If there is any question about any part of this, please let me know so I elaborate on. Thank you.
So it's 5 minutes to 4 and the bus is waiting probably at 4 o'clock. So any question? One more question for me then.
Sure.
Yeah, why did you choose to use Bayesian networks and not other type of models?
Because the Bayesian network allow for modeling causality. For if you use other methods, let's say regression model or neural network model. So what they do, they model the relationship between the very first input and very last output. So that's fine for modeling part. But when it comes to intervention, suppose that we want to affect one of the variables, for example, financial loss. Yeah. So we cannot assume that only one variable changes and the other remains the same. Why? Because one value can affect the value of other variables. So as long as modeling is the case, you are right, and there are much better options. But when it comes to intervention analysis, where we want to change one variable, we need to consider what other variables are also changed automatically because of that. Therefore, we need to know the causality between the variables, and causal Bayesian network is one tool to do that.
Okay, any other questions? No? Then we should conclude our session. Thank you very much.
Thank you.